Imagine waking up one day in the middle of the ocean. Everywhere you look, there is nothing but endless water. The nearest shoreline is hundreds of kilometers away. Beneath you lie dozens of meters of seawater, powerful currents, and a soft seabed. At first glance, building anything here seems impossible. Yet today, these very locations are home to airports, seaports, residential neighborhoods, luxury resorts, and even entire cities. The most astonishing part is that just a few years ago, not a single square meter of land existed here. Everything you see was created by human hands. But how do engineers literally build new land in the middle of the ocean? Where do millions of tons of sand and rock come from? Why do some artificial islands cost tens of billions of dollars? And what happens if even one stage of construction is carried out incorrectly? Today, we'll explore the entire process of creating artificial islands, step by step, from the very first surveys of the ocean floor to the construction of fully developed infrastructure capable of withstanding storms, typhoons, and even powerful earthquakes. The construction of any artificial island begins long before the first bucket of sand is dumped into the sea. In fact, the first stage takes place not at the construction site, but inside research laboratories and aboard specialized scientific vessels. Engineers must first identify a location suitable for future construction. At first glance, the ocean may appear uniform, but beneath the surface lies a dramatically varied landscape. In one area, there may be solid bedrock capable of supporting enormous loads. In another, there could be a thick layer of soft silt that gradually compresses under the weight of the future island. Sometimes, hidden voids or weak soil layers beneath the seabed make construction far too dangerous. To study the seabed, engineers use advanced sonar systems. These devices emit sound waves that bounce off the ocean floor, allowing them to create highly accurate three-dimensional maps of the underwater terrain. Next, drilling platforms extract long core samples from depths of several dozen meters beneath the seabed. These samples are sent to laboratories, where specialists analyze their composition, density, moisture content, and structural strength. But studying the soil is only part of the challenge. Engineers must also account for ocean currents, prevailing winds, wave heights, tidal ranges, the likelihood of typhoons, and in some regions, even the risks of tsunamis and seismic activity. All of this information is combined into sophisticated computer models that predict how the future island will behave not only in the coming years, but over the next 10, 20, or even 50 years. If the analysis reveals an unacceptable level of risk, the entire project may be canceled before construction even begins. The cost of making a mistake at this stage is simply too high. Once construction starts, relocating the island is no longer an option. After the ideal location has finally been selected, engineers move on to the next stage, preparing the foundation. This is where they face the first major engineering challenge. Ordinary sand dumped into the sea is immediately washed away by powerful currents and settles unevenly across the seabed. Building an island is therefore far more complicated than simply pouring sand into the water. To overcome this problem, engineers rely on advanced ground stabilization techniques that strengthen the seabed before any large-scale land reclamation begins. Without these technologies, construction would never be possible. It is at this moment that the transformation of the open ocean into entirely new land truly begins. Once the research phase is complete, construction enters its most spectacular stage, the creation of the foundation for the future island. It is here that these projects truly reveal why they are considered some of the most complex engineering challenges in the world. The first obstacle is the seabed itself. In many locations, it consists of soft silt and loose sand that simply cannot support the weight of millions of tons of construction material. If engineers begin dumping fill material immediately, the ground will gradually sink, and the future island could slowly disappear beneath the sea. To prevent this, engineers must first stabilize the foundation. Special geotextile fabrics are laid across the seabed, acting like a giant reinforcing blanket. These materials prevent the sand from mixing with the soft silt below while significantly improving the stability of the foundation. In some projects, thousands of vertical sand or stone columns are installed deep into the seabed using powerful drilling rigs. These columns accelerate soil consolidation and allow trapped water to escape from the deeper layers of the ground. As a result, the soil becomes much stronger and capable of supporting enormous loads. Once the foundation has been prepared, the next challenge begins: delivering the construction material. But where do millions of cubic meters of sand come from? Ordinary trucks are useless in the middle of the ocean. Instead, engineers rely on massive dredging vessels that operate around the clock. Equipped with enormous suction pumps, these floating machines extract sand from the seabed or from offshore borrow areas located dozens of kilometers away from the construction site. The mixture of sand and water is then pumped through long pipelines directly to the construction area. Every single day, these dredgers can transport tens of thousands of cubic meters of material. Within just a few months, the total volume of sand placed can reach several million cubic meters. However, pumping sand alone is not enough. Once the mixture reaches the site, the water gradually drains back into the sea, leaving the sand behind. Heavy construction equipment then spreads and compacts the material layer by layer. Each layer undergoes strict density testing. If the ground fails to meet the required specifications, compaction continues until the foundation reaches the necessary level of strength and stability. As the island gradually takes shape, engineers encounter another major challenge: protecting it from the relentless power of the sea. Even a relatively small storm can erode a newly reclaimed shoreline. To prevent this, massive coastal protection systems are built around the island's perimeter. Giant boulders weighing several tons each are carefully stacked together to form breakwaters. Their shape and arrangement are precisely engineered so that incoming waves lose much of their energy before they ever reach the shoreline. In areas exposed to especially harsh ocean conditions, engineers use enormous concrete armor units with unique interlocking shapes. These specially designed blocks lock together, creating an extremely stable barrier capable of absorbing the tremendous force of even the most powerful ocean waves. Slowly, the outline of the island becomes more defined. What was once nothing but open sea now begins to resemble a genuine piece of land. But in reality, construction is only just beginning. The next challenge is even greater: ensuring that this artificial island remains stable not only today, but for decades to come. Despite the constant pressure of its own weight, the gradual movement of the ground beneath it, and the relentless forces of the surrounding ocean. Once the island begins to take shape, many people assume that most of the work is already complete. In reality, however, this is where the most challenging phase truly begins. Simply placing millions of tons of sand is not enough. Engineers must ensure that this newly created land remains stable for decades, or even centuries. The biggest challenge is that freshly reclaimed sand contains large amounts of water and trapped air. Under its enormous weight, the sand gradually compresses, causing the surface of the island to slowly settle. If buildings, roads, or airport runways are constructed too soon, they may develop cracks or even suffer structural damage within just a few years. To prevent these problems, engineers use advanced ground improvement techniques to accelerate soil consolidation. One of the most effective methods is vacuum consolidation. The surface of the reclaimed land is covered with an airtight membrane, while powerful pumps create a vacuum beneath it. This process rapidly removes water from the soil, making the sand significantly denser and far more stable. Another widely used technique is preloading. Engineers temporarily place millions of additional tons of sand on top of the newly formed island. This extra weight speeds up the natural settlement of the ground. After several months, or sometimes even years, the excess sand is removed, and only then does construction of permanent infrastructure begin. At the same time, engineers continuously monitor the condition of the island. Specialized sensors are installed across the entire site to detect even the slightest changes in ground elevation. In some cases, settlement is measured with an accuracy of just a few millimeters. If the measurements differ from the predicted values, construction plans are immediately adjusted. Once the foundation has reached the required level of strength, work begins on the island's underground infrastructure. Beneath future roads, engineers install kilometers of pipelines for drinking water, sewage systems, and stormwater drainage. At the same time, power cables, communication lines, and high-speed fiber optic networks are carefully laid beneath the surface. One of the greatest engineering challenges is protecting the island from flooding. During heavy rainfall or severe storms, enormous amounts of water can quickly accumulate on the surface. To prevent flooding, powerful pumping stations are built to operate around the clock, continuously draining excess water back into the sea. The next stage is road construction. Even here, specialized engineering techniques are essential. Each road is built on multiple carefully designed layers of sand, crushed stone, geotextile fabric, and high-strength asphalt. This layered structure distributes heavy loads evenly while preventing the road surface from sinking or cracking over time. If the island is intended to include an airport, the engineering standards become even more demanding. The runway must remain perfectly level throughout decades of operation. Even the smallest amount of uneven settlement can pose a serious safety risk for aircraft. For this reason, airport foundations undergo additional reinforcement and multiple rounds of rigorous testing before they are approved for use. Gradually, what was once nothing more than a lifeless stretch of reclaimed sand begins to transform into real land. Roads, bridges, power lines, utility systems, and the first buildings start to appear. Yet one final challenge still lies ahead: creating a fully functional city capable of thriving safely in the harsh environment of the open ocean for many decades to come. Once the island's foundation has been fully stabilized, construction enters the stage that most closely resembles building a conventional city. In reality, however, the conditions are far more demanding. Every building, every road, and every utility system must be designed to withstand constant exposure to salt water, powerful winds, and extreme weather conditions. Before the first buildings are constructed, engineers once again evaluate the load-bearing capacity of the ground. Even after years of soil consolidation, certain areas may continue to settle unevenly. For this reason, large structures are often supported by deep foundation piles that pass through the reclaimed sand and anchor into much stronger rock layers buried deep beneath the seabed. The next major challenge is creating a complete life support infrastructure. Since artificial islands have no natural source of fresh water, most modern projects rely on advanced desalination plants. Seawater passes through multiple stages of filtration and purification before becoming safe for drinking and everyday use. A reliable energy supply is equally essential. Electricity can be transmitted from the mainland through submarine power cables, but many artificial islands also operate their own power plants. Increasingly, these projects incorporate solar panels, wind turbines, and advanced energy storage systems to reduce dependence on external power sources and improve long-term sustainability. Engineers also place special emphasis on protecting structures from corrosion. Salt carried by the sea dramatically accelerates the deterioration of both steel and concrete. To combat this, builders use specially formulated marine-grade concrete with enhanced resistance to salt water, while steel components are coated with multiple layers of high-performance anti-corrosion protection. At the same time, construction continues across the island. Roads, bridges, residential neighborhoods, hospitals, schools, shopping centers, and public spaces gradually take shape. If the island is designed to serve as a major international airport, engineers build modern passenger terminals, air traffic control towers, fuel storage facilities, and kilometers of taxiways. If the project is focused on tourism, luxury resorts, beaches, artificial lagoons, parks, and yacht marinas begin to emerge. Yet even after construction is officially complete, the engineer's work is far from over. Sophisticated monitoring systems remain active throughout the island, continuously measuring ground settlement, internal foundation pressure, shoreline movement, and the condition of coastal protection structures. Every major storm becomes a real-world test of the island's engineering. If waves prove more powerful than anticipated, seawalls and breakwaters are reinforced with additional rock armor or newly designed concrete structures. Continuous maintenance becomes just as important as the original construction itself. It is this ongoing commitment that allows an artificial island to evolve into a fully functioning extension of the natural world, a place where hundreds of thousands of people can live, international businesses can thrive, and dozens of aircraft can land every day. Yet even these extraordinary achievements require constant vigilance because humanity's battle against the ocean is never truly over. After years of planning, millions of tons of sand and rock, and thousands of hours of continuous work, the moment engineers have been waiting for finally arrives. The artificial island is officially ready for operation, but in reality, construction is never truly finished. Unlike natural land, an artificial island is in constant interaction with the ocean. Waves slowly erode the shoreline. Powerful currents reshape the seabed. During storms, massive volumes of water relentlessly test the strength of coastal defenses. That is why, even after construction is complete, engineers continue monitoring the island around the clock. Hundreds of sensors are installed throughout the island. They measure ground settlement, shoreline movement, soil pressure, groundwater levels, and even the slightest structural displacement. All of this data is transmitted in real time to centralized control centers. If the monitoring system detects even the smallest abnormality, engineers can respond immediately, often long before a minor issue develops into a major problem. In some areas, the shoreline must be reinforced with additional rock armor. Elsewhere, fresh sand is regularly added to replace material lost through natural erosion. Pumping stations continuously regulate water levels within the island, while drainage systems remove excess rainwater after heavy storms. Special attention is also given to the growing challenge of climate change. Rising sea levels have become one of the greatest threats to coastal engineering projects worldwide. As a result, modern artificial islands are designed with decades of future environmental change in mind. Their seawalls are built higher, drainage systems are made more powerful, and protective barriers are engineered to withstand increasingly severe storms. Despite their enormous cost, many countries continue investing in artificial island projects. The reasons vary. Some nations simply lack enough available land for new airports, seaports, and residential developments. Others expand their territory to support economic growth. Still others build artificial islands to host major industrial facilities, energy complexes, or international logistics hubs. Meanwhile, the technology behind these projects continues to advance. Engineers are developing more environmentally responsible methods of dredging sand, designing new materials that better resist the corrosive effects of seawater, and introducing artificial intelligence systems capable of continuously monitoring an island's structural health. In the future, these projects may become even more ambitious. Some experts are already exploring the possibility of fully autonomous floating cities powered entirely by renewable energy. Others are researching adaptive artificial islands capable of responding to changing sea levels and evolving environmental conditions. Only a few decades ago, the idea of building a fully functioning city in the middle of the ocean belonged to the realm of science fiction. Today, it is an engineering reality. Artificial islands have become a powerful symbol of how far modern technology has progressed. They demonstrate that with scientific knowledge, precise engineering, and an extraordinary amount of human effort, it is possible to create entirely new land where nothing once existed except the endless expanse of the sea. And perhaps, in the decades ahead, these remarkable islands will become the foundation for new airports, megacities, and entire regions that will permanently reshape the map of our world.